told you that an enzyme and a substrate bind together and form an enzyme substrate complex. And I said that the substrate or substrates always bind at the active site, right? Okay, so what I did on the board behind me is I oversimplified, but I just sort of wanted to give you a visual of what is going on. All right, so pretend that all this black stuff over here, that's my hypothetical enzyme. Remember, it's a protein. It's got an alpha helix, some beta pleated sheet. It's got a three-dimensional structure and a final structure that is absolutely perfect. Okay, there are a few amino acids, these could be 3 or 4 amino acids, that are considered the most important ones, and this is the active site. So that active site has to be there for a substrate to bind, all right? And it has to be in the exact right shape. Like, that's why if you denature an enzyme, the shape is altered, it gets unraveled, and the active site is no longer there, and the substrate can't bind. So in this little oversimplified hypothetical, this is my enzyme. Can you see this shape of the active site? And this substrate is going to fit right in. Now, if I had another substrate that was a circle, that's not going to fit. So imagine that this is the enzyme sucrase, like the example I gave you in the earlier video, and you've got, this is sucrose, and maybe in here's a molecule of water. They both fit right in. The water and the sucrose collide, the glycosidic bond breaks, and now we have glucose and fructose. That's part of digestion. And let's pretend this dude over here is lactose, and your body doesn't have any lactase, so it says, no big deal, I'm going to use sucrase to hydrolyze me. It won't work. Why won't it work? Because this doesn't look at all like the active site, all right? So the active site has to look like the substrate so the substrate can fit right in. All right, so the models or the theories or how they explain all this, there are 2 ways of looking at it. Lock and key model, that's the model where the active site has to look exactly, verbatim, like the substrate. So exactly like. So if this is a box looking thing or a rectangle, then the rectangle can fit. End of discussion. All right? Very, very, very specific. Like, a key that fits in a lock. Have you ever tried to make a copy of a key and then the copy doesn't fit in the lock, even though it looks the same? So lock and key is that specific. The original key with the original lock, that is it. Induced fit just means that your enzyme will accommodate a little bit. It'll move a little bit to allow the substrate to fit. Not to the extent that it'll allow this guy to come in. I mean, it's completely different. So, but let's say if the enzyme was closed off a little bit, just, I'm going to do a little bit of a hypothetical here. So let's say instead of a perfect rectangle, enzyme sort of looked a bit like this. And then this is the substrate. So it's still a square or whatever wants to get in. You know what can happen? The enzyme will move slightly, will move gently, and allow the substrate in. I tend to personify these things and imagine them as real people, but this is just an enzyme. So it has the ability of adjusting, and that's what they call induced fit. Induced fit means that it will sort of force the fit. But again, I warn you, it's not to the extent of getting a completely wrong substrate. It won't accommodate this guy, but you see how this is sort of grooved in a little bit? It will open up, it can move, open up, and again, I'm definitely not an artist, but then this guy can fit, all right? So induced fit is probably the way most enzymes are. They're a little bit more flexible than the lock and key. All right, now, what is inhibition? There's 2 types of inhibition. There's competitive inhibition. I'm going to erase this. There's competitive inhibition. And there's non-competitive. Let's first talk about competitive inhibition. Okay, what is competitive inhibition? The word inhibition means to prevent or to stop. Okay, so an inhibitor molecule is a molecule that will prevent this enzyme from working. All right, and we've got lots of inhibitor molecules that we use in the health fields, like, have you ever had to take antibiotics? An antibiotic is an inhibitor molecule. It will inhibit the enzyme of the bacteria, all right? And then then the bacteria ends up dying, all right? So again, lots and lots of things like that. All right, so how does this work? So the cool thing about competitive inhibition is that I, which is the inhibitor molecule, looks like the substrate, okay? Which makes sense, okay? So the inhibitor molecule looks like the substrate. So let's pretend that this is the substrate and this is the inhibitor molecule. This is the substrate, this is the inhibitor. See how they look very similar? All right, so if I've bombarded my body with plenty of inhibitor, the antibiotics, I took the whole course, I didn't skim. The inhibitor will compete with the substrate for the active site. Who's going to get there first? Well, if the inhibitor gets into the active site before the substrate, it binds to the active site, does not allow the substrate to get in. If the substrate can't get in, the reaction stops, okay? If, on the other hand, you have plenty of substrate and you just keep adding more and more substrate, then you could probably reverse this. So that's why they tell you, make sure you finish your course of antibiotics, because you want to make sure the inhibitor, you've got more of it, and you end up stopping that enzymatic reaction for good. It all has to do with the bacteria creating more cell walls, and in order to replicate, it needs a cell wall. Anyway, bottom line is, know that in competitive inhibition, the inhibitor molecule mimics the substrate, looks just like the substrate, and it fits into the active sites, and it stops the enzyme from working. It inhibits, stops the enzyme, okay? So that's competitive inhibition. What's the other type of inhibition? The other type is called non-competitive inhibition. So non-competitive inhibition. Okay, so what is that? Well, in this case, the inhibitor, so inhibitor does not look like substrate. Okay, great. So the inhibitor doesn't look like substrate. Well, then there's no way on earth the inhibitor is going to bind to the active site, because the active site is a specific shape, and only the things that can fit in that shape will fit. And it's not going to adjust to allow this guy in. So what happens in non-competitive inhibition? This guy, it binds to an alternate site. Hope you guys can read this stuff. So it binds to an alternate site. That means a site that is not the active site, okay? So can you see that it could potentially bind right here? So this guy comes and binds right here. All right, what happens when it binds? This is so incredible, so cool. When it binds to the alternate site, I'm gonna write it over here. What happens? The minute the non-competitive inhibitor binds to an alternate site, this is another site on the enzyme. It's not the active site. Why doesn't it bind to the active site? Because it doesn't look like the active site, okay? It binds to an alternate site. Once it does that, then the enzyme changes its shape. So fascinating. How cool is that? So the non-competitive inhibitor binds to an alternate site, the enzyme changes its shape, and then guess what? When it changes its shape, the active site now has changed its shape. So instead of having an opening to allow that hypothetical substrate to come in, once this non-competitive inhibitor binds here, now the active site is blocked off. Not by the non-competitive inhibitor, but by the fact that the enzyme, because you remember that whole induced fit, enzymes are a little mobile. Once that non-competitive inhibitor binds to the alternate site, the active site is changed, and so now the substrate cannot bind. And if the substrate can't bind to the active site, no reaction, okay? The fascinating thing about this, though, is it's reversible. With competitive inhibition, it's really hard to reverse. But this one, the minute the non-competitive inhibitor leaves, the enzyme goes back to its original shape, and the substrate can bind. Your body uses non-competitive inhibition in a lot of pathways. We'll talk about pathways in the next video, but you should know from this video the terms lock and key, induced fit, competitive inhibition, and non-competitive. And know that competitive inhibition is when the inhibitor molecule looks just like the substrate and they both compete for the active site. In non-competitive inhibition, the inhibitor molecule does not look like the substrate. It binds to an alternate site on the enzyme. The enzyme just then changes its shape, blocking off the active site, so now the substrate can't bind, and you've just inhibited the enzymatic reaction. Okay? And like I said, next video we'll talk about pathways and how this non-competitive inhibition can actually regulate some pathways. Okay, see you in the next one.